Right. Okay. So here I'm mostly the messenger. I'm a co-author, but this is really mostly the work of the other three guys. In particular, one of my most brilliant students, Daniel. For various funding, travel, budget reasons, none of them could make it, so you have me. This is similar to what Andre said. So this is not using any machine learning. It's trying to make the best out of what we currently have and trying to get the best out of the CPUs. And this is mostly about vectorization. So this is a bit what I'm going to tell you. So for introduction, okay, you have seen that most of you have been probably listening to Rosen and to Mazo, so I'm not going for this. I mean, this is motivated in part. It's in its own right interesting, as has been also said by Liz this morning. We have to make our software faster. But in the case of LHCb, it's of course motivated specifically by our upgrade, which is due in 2020. And we will need every last bit of CPU we can get. Right, so I've said that. So this is a bit in this context of also this is a collaborative work we did together with Intel, and that's why we have also a co-author from Intel Labs in Paris who was doing this together with us. Right, so this is an overview. Have you seen it? This is similar. I guess this exists for every LHC experiment, but this is an overview of the LHC code base. So depending on where you count, I mean, where you start counting our code base, as you all know, this is a huge code base, many million lines of C++ code. There is currently, this has been told by Stefan in his presentation, a large effort going on to redo our computing framework to make it more vector-friendly, to make it more cross-platform compatible. And because as all the frameworks, it's currently based on, the current framework was based on a single-threaded x86 kind of architecture, and so this is moving on. The new framework, like I think in all LHC frameworks I've heard about, will use TBB, and it's a kind of task-based approach. And we are also checking other things a bit more off the mainstream by offloading critical functions to FPGAs and rewrite time-consuming algorithms potentially completely parallel by using things like Xeon-Phi. This is just a heat map of our things. What is important here is that the most important part, and this is in particular interesting in the trigger, is the tracking. Tracking is about 60% of the overall time spent in our code. So that's why this work is focusing here on the tracking. So Cross-Kalman is a project to study. It's called Cross because the emphasis was here to really be able to study, make a version of the Kalman filtering, which is the key part of our track fitting, which is across many architectures, so that we can compare the merits of to evaluate the relative merits of architectures. Because one thing is to read the spec sheet of various, KNL and GPUs. The other thing is to see how much it can actually bring you in an application which you have to do, which you can't choose, because the problem is what it is. So I'm not going to explain the Kalman filter here again. I think most of you know, and many of you certainly know this better than me. Essentially, this is an iterative least square kind of approximator, and so it consists of predict and update states. And in LHCb, we have two types of nodes. So we represent the tracks which have been found by the pattern recognition by nodes, and nodes are either signal nodes. This is where you had a measurement, or we have also reference nodes. This is which we interpose between. If the signal nodes are too far apart, we have reference nodes in between where we just extrapolate, but we have no measurement. Okay, this is in order to cope with areas where in LHCb there's no tracking in the magnet. This is a large thing. So this has certain algorithmic complications to it, not necessarily mathematical ones, but algorithmically this is important. So this architecture was made. So here was not the idea to in any way improve the Kalman filter as an algorithm as such. The idea was here to try to make the best out of the vector engines at hand. And so I'm discussing a little bit the control flow, the data structure, and then I'll go to the performance figures. So I said that every particle, or every track, if you like, is a succession of nodes, essentially. So can you imagine this is a list of nodes, which can either be, as I said, signal nodes or or prediction nodes. And now, when you want now, so you have many tracks in parallel. Okay, so you can, in principle, treat. You cannot treat the track is an iterative thing. So you have to go through the nodes in the prescribed list. But the tracks are independent. So you can treat multiple tracks in parallel in a vector engine. Now, of course, not every track has the same number of nodes. Otherwise, it would be relatively simple. So if you want to keep your vector engine busy, you have to arrange these lists of nodes such that you keep the vector, that you always have something for the vectors to do. So this is a number partitioning problem. And like many simple numerical problems, it's surprisingly complex. So this is actually a proven NP-hard problem. So there's, on the other hand, okay, you can Google this a bit. There are heuristic algorithms, which this is also again true for some of for quite a few NP-hard problems. That there is a few heuristic algorithms which actually do quite well in practice. That's the case also here. So we used this decreasing time algorithm to sort the algorithms. This is how this looked like for our scheduler. So I always have to think that I won't get this wrong. Essentially, what this is you can see here. This is essentially the particle number and the node number. And you can see here. So this is this is an AVX machine because these are all double quantities. So it has sort of 4 tracks in work. So the vector is working on 4 tracks. And you can see here that all the vector engines, sort of the slots, are busy. And you have one which is about to finish because this is the last node. It's outgoing. It's the last one. And it will not figure here. And here you have a new one. So the 113 is finished. 79 is entering. Okay. So that's what this sorting is supposed to do. That here you have always ones, not that all the lines are busy. That's the whole idea. And another thing which is important in this, of course, is that you have a data structure which maximizes data locality. So we have an array of structure of arrays. And so what you need in the Kalman fit, essentially you have the 5 track parameters. Then you have the covariance matrix, which is 15 parameters. And you have a chi-square for the goodness of the fit. And so you see this here. These are entered here in a form that you have for your 4 vector entries. They always come like this, that they can feed directly into the vector. Okay, so you have and then here you have the matching comes the next one. So you have an array of a structure of arrays. So that first of all guarantees alignment and also guarantees the locality for the engine. So for the arithmetic backend, to be able to use a lot of these kind of things, we have tried various vectorization engines. CUDA is actually much more obviously than a vectorization engine, and OpenCL as well. And so in the next one, I will show a few of those. So this is a bit the due diligence on the things. In the meantime, of course, we have everything also with GCC 7.2. This is, of course, once you have this, you can, of course, amuse yourself with running it with the newest compiler. So all this is using LHCb events properly done, and there's also these events have been compared against the production version of the track fit, so to make sure that actually it does the same in terms of physics. So this is not cheating. So this is not a toy example. It gives physically. I mean, the quality of the physics results is equivalent. So 5,000 events. The NUMA pinning was done by hand, but properly as it was necessary. And in order to really max out to measure a machine, TBB was used to launch as many instances in parallel to work on events so that the machine is fully busy in order for the benchmarking to actually load the respective engine. So these are, I'm not going through this here, but so this is the zoo of machines we have been using. This one is interesting. Just want to mention this one here. So this is a typical machine which is very widely used also in CERN IT. So most of the batch nodes, if you land on one of the CERN batch queues, on the newer ones will land you on this. And this is also the bulk node which we have in LHCb in our trigger farm. This is something a bit fancier. And then we have this Xeon Phi's. And this is something you can never dream of affording. This is sort of unimaginably expensive. I mean, it's even here. So this is the list price from Intel. Now, our friends from Microsoft don't pay this, of course, but anyhow. But it gives you an idea. No, but the discounts are normally linear. Right. So So this is the speed up. So this is the scalar performance. So this is the unoptimized algorithm as it runs, and then we compare now the speed up we get when we on various things. And so you see here that with the improvement of the, so this here has more cores, but the same vector width, and you get a speed up of 36% here, factor 2 here. But here, of course, you have more cores. And here you have a Xeon Phi. So that's a machine which is really geared for vectorization. This has an AVX512 engine. And here you have the Skylake, which has also the AVX512 engine. Okay. Now, yeah. Okay. So these are the speedups you can achieve. That's another one. So this is interesting for me. So I'm usually very blunt. No? I'm asking of what it actually brings in terms of money, because in the end it has to pay off. I mean, and and that's the first question to ask. Huh? I mean, is it worth it? And surprisingly, if you think now what it costs to get 10,000 events through, you find out that the Xeon Phi doesn't look so bad. That's surprising. There's a catch to this, of course, like always. Intel was happy to see that. Obviously, this here doesn't look so good. I mean, this clearly shows that, I mean, you have to have a crazy licensing software to justify that kind of CPU. So why does the Xeon Phi do so well? So here is another thing here, which before we go to that, you see here the throughput in terms of, so this is the scalability as you activate threads, and you see that most of the things scale quite well as long as you use physical cores, and then the hyperthreading gives you a little bit, but not much. It's a log scale, so it gives you still something. It is good. I mean, if you had perfect arithmetic density, if you could fully keep the processor busy, then hyperthreading shouldn't help you at all. Okay, so actually that hyperthreading helps is a bad side. No, I mean it shouldn't help. No, so the less hyperthreading gives you, the well, I mean, this is a bit exaggerated, but in general, I mean, hyperthreading essentially means actually that your processor is waiting for I/O. So here we have a little artifact. I'm preempting the question that it's not fully understood, but it's believed also by our Intel friends to be a caching issue. This is this little overshoot here for the Skylake. But also most of the other nodes, most of the other architectures behave as you would expect them to behave. The Xeon Phi, of course, has a lot of hyperthreads because it's actually 4 hyperthreads, so the effect is a bit stronger. So you see, 72 is the point where you leave the number of physical cores, and then you have a sharp drop as you start activating the threads. Okay, so we have even a newer. So this is a comparison how this does with various compilers. So we have here GCC 7.1, Clang, and ICC. And yeah, ICC is doing a little bit less good than the others. So this is, we have this somewhere in the works. The parallel efficiency, so but there's no, you know, except for maybe a few odd points out, there's no huge difference. And also still it's a log scale, no? So I mean, but okay. As it seems that at high core counts, the differences between compilers seem to even out. But GCC seems to be a little bit ahead, at least for these versions. No? Okay, so this is our results now in our new multi-threaded framework, the one Stefan has mentioned in the prototype. So, and what we see here is that here, if you compare the architectures, here the Xeon Phi doesn't look so good anymore. No? It loses compared to the, so the losses are quite a bit stronger. This means because the full Gaudi framework obviously has to do a lot of other things which are less nice to the lightweight cores which the Xeon Phi presents. And so, well, that's the reason why we use Xeons, not Xeon Phis right now. Still, it is interesting to see that if you just look at the algorithm alone, such a highly vectorized parallel architecture can give you a lot of benefit. And once you switch on everything else, you tend to lose a bit. So the suspicion is, so this is also substantiated by some benchmarking, is that this is mostly memory contention. Okay, this is a roofline model, which is another way of looking at the performance and the arithmetic density, which you can see here for the various parts of the algorithm. So you see here, these are the theoretical floating point performances which you get from the data sheet out. and here the memory bandwidth of the machine can achieve. So we actually do well. I mean, we manage to be better than what the pure DDR gives us. Okay, for the Skylake, it is difficult. We also didn't have a lot of time to optimize it because we only got the remote access for a few days. But here it really looks like that because there are so many cores in this Skylake that you need a very, very compute-intense code to be, because the memory bandwidth most of the Xeon models is the same. And you have always channels, and if the memory is a bit faster, but it doesn't matter. Essentially, you find the obvious fact that there's more and more compute units competing for the memory. It's not really a problem because we can anyhow not afford this CPU. So in reality, this is a kind of a non-issue, but it's interesting to see where the limitations are. Conclusions. Okay. So we have now a working cross-architecture benchmark for the Kalman filter for LHCb. It seems to work well on modern SIMD architectures, and we can integrate this in our software framework. So this has been backported into the current used Gaudi framework. And we are now checking which of the architecture. This is an important decision is when we want to buy the next generation of farm nodes. It's interesting which ones will give us the best performance. Memory has a big impact, so what next thing is to see is if a lower latency or higher bandwidth memory can have a beneficial impact. And this will be, for example, like Micron's hypercubes. So this is one of the things which will be evaluated in the near future. Of course, there's never a simple answer, but at least we have now a tool which is sort of benchmarking something which we really need rather than a purely synthetic benchmark. Questions? Thanks.
So since this has been tuned for the SIMD architecture, I would imagine it also works quite well on a standard graphics processor.
Yes.
So have you looked at and compared the price per performance?
So because we have an Intel Core, we have to drop all the results on non-Intel architectures because the Intel Ligue is worried to show with an Intel Core. But I can show you these results. So we have Power 8, and we have also graphic cards with those. Power 8 performs as you would imagine, roughly. I mean, and AMD performs quite well. We have some results also on the new EPIC cores. Other questions?
There might be another question.
Andre. And then we can discuss in the coffee break. Yeah. There's no coffee break?
No, there is a coffee break.
Well, after. Eventually. Eventually, yeah. Yeah, I just said eventually. During.
Nico, in GNV we are doing more or less same. We have to play getting data into a sort of a SOA form or AOSOA for vectorization. And in my experience, there is kind of an overhead to do the data gathering from wherever you have it.
Definitely. This is a good point.
Have you measured this? Profiled your application?
Yes, there's an overhead. Yes. I don't have the numbers here, but Daniel has measured this. Yes, so there's an overhead, and that's one thing which we try to feed back in the overall framework, that maybe we get the formatting done once, no? And we try to keep things together. It depends a bit when the data and where the data is created, so that when these structures are actually populated and for the first time, that they are put in this form, so that you pay this price only once. Because clearly, if you have to reformat them into this to make it work, then you pay this is costly, yes, indeed. But this is one of the key costs, definitely. Okay.